This is the seismic refraction survey. So we've set up equally spaced geophones along a wire. This is a geophone, which is the sensor for our seismic survey. So remember, there's a magnet with a coil in it. So when the magnet moves, we're going to be inducing a voltage. What we're going to do is we're going to place this into the ground, and we can stamp on it to make sure that there's a firm connection with the ground. And then we connect the wires up to the cable which has all of the geophones on it. This is relatively easy because there is a big gap and a small gap, so you can put the big clip onto the big clip and the little clip onto the little clip. This just makes sure that all of the geophones are recording the voltage in the same direction when we put it into the geode. After laying out the cables and connecting the geophones, the next thing to do is to connect everything up to the geode. This is a digitizer and will combine the signals in the best way possible. Firstly, we need to plug in the geophone cable. This cable has a lot of individual wires within it, which each have their own pin for the geode. Geophone 1 would have the pins small a and capital A, and geophone B would have the pins small b and capital B, etc. This allows the geode to know exactly which geophone the voltage is being produced by. There is only one way to plug in these cables, but you have to be careful not to damage them. You do this by lining up the pins correctly. Each wire has up to 24 geophones on it, but you can connect more geodes together to increase the line of geophones to 48 or more. As well as the geophones, you can add the hammer or source, which provides a starting signal or time zero. The voltage produced by the hammer strike is from the compression of a piezo-ceramic material attached to the top of the hammer. Alternative sources could be explosives or a large weight that is dropped. We also attach a cable that connects the output of the geode to a computer via the Ethernet cable and a battery. Here we have the Toughbook computer. This is a special laptop that is waterproof and mostly drop-proof and has the correct software. The first thing we need to check is that every geophone is measuring a signal. We are next to a road outside Grant, so there is a lot of traffic, or alternatively we can have members of the team run up and down the line. You can see from these squiggles that there is a reading being taken at the 5 geophones that we have laid out, but there is no signal from the geophones that are still on the drum. After we have checked that the geophones are connected correctly, the next thing to do is to move into shot mode. We can arm and disarm the hammer, so it is good to check the hammer is ready by the green bar at the bottom. We can now strike with the hammer. From this, you can now see we have recorded a signal at the first 5 geophones. The signal after this is just electrical noise, so you can ignore them. We can see it is still quite noisy, so we can improve the signal by stacking and repeating the number of hammer hits to get a cleaner signal. The signal to noise ratio improves at a rate of 1 to square root number of hits. We are interested in the first arrival, which will either be the direct wave or the refracted wave through a deeper, quicker layer. Once we have completed the shots in this direction, we would move the source to the other end of the line of geophones to investigate whether our subsurface is dipping. Our source is a hammer, which the trigger time will start in the geode when the piezo-ceramic material is compressed. And to do a good hammer strike, we want to just lift it up and strike the base plate cleanly without having any double bounces. You will have to wear ear defenders if you are doing this for a long time.